Hello guys, hope you all are doing well. So in the continuation of the previous GATE series, we are solving GATE questions of GATE. We have completed 1999, 2 marks question are remaining and more. And today we'll see section B of 2000 because section B is a little bit important. So without wasting time, we'll see what's first question. Find the directional derivative of u. We have a scalar. Okay, u at point 1, 2, 3 in the direction 1, 2, 3 to 1, minus 1, minus 3. Okay, so directional derivative is given by this del u. So del is this, u is our scalar. So putting value, we will get this. Now in the direction 1, 2, 3, 1, minus 1, minus 3. So we have to find out the direction ratios. So direction ratios are this 0, 3, 6. So the required direction is 0i plus 3j plus 6k. So this is the directional derivative. Okay, required directional derivative. Okay, so straightforward question. Second question, find whether or not the vectors 1, 1, 2, 1, 2, 1, 0, 3, minus 3 linearly independent. To check whether the vectors linearly independent, the rank of the matrix should be equal to number of the rows. Okay? So linearly independent condition, the number of the rank of the matrix which is formed by the vectors should be equal to the number of the rows. So here are 3 rows. And in the previous lecture, while solving 1999 section A, I told you that a rank of a metric, a rank of a metric is R if R plus 1 determinant is equal to 0. That means we have here 3. So 2 plus 1, that is 3 cross 3 determinant equal to 0, which is 0. So the rank will be 2. Okay, the rank will be 2. And the condition is every 2 cross 2 determinant should be non-zero. So very first 1, 1, 1, 2 is a non-zero, which is sufficient. Okay, so rank of the metric is 2. And for linearly independent, rank should be 3. So this is linearly dependent vector. Okay, so straightforward. Since this question GATE has asked in 2000, so you have to prove by stepwise, by solving complete determinant or a complete like you have to show. It is a 5 mark question, so you have to show. Okay, so next question, industrial grade methanol can be produced according to the reaction CO plus 2H2, that is CH3OH. For this reaction, del G at 400 Kelvin is equal to this. If an equimolar mixture of CO and H2 is fed to the reactor maintained at 400 Kelvin and 10 bar pressure, determine fraction of CO that is converted into CH3OH. Okay, so we have to find only extent of the reaction. So very first, this is the reaction, and let E be the extent of the reaction. Okay, so we have to find the E at T equal to 0 when the reaction is not started. 1 mole CO, 1 mole H2. This make an equimolar mixture of CO and H2. Since the reaction is not started, so 0 mole CH3 at T equal to T after completion of the reaction. Let's suppose E mole CH3OH produced. So how this term will come? H2 reacted will be 2 upon 1 into E is equal to 2E. H2 fed 1. H2 unreacted, 1 minus reacted equal to 1. So 1 minus, this is unreacted. Similarly, CO unreacted. Okay. So total moles at equilibrium, we have this. Okay. Now, mole fraction of CH3OH, H2 and CO. Sorry. Okay. So we know that Kp is equal to K by P summation of nu. Every year GATE is asking this type of question. Okay. So putting all the values, we will find the value of K. See, kilojoule cancel out. mole cancel out, Kelvin cancel out, this K will remain and it is 1000. So we will multiply it in the numerator as 1000. We will get this. Okay. Now summation of nu, that is the summation of the stoichiometric coefficient minus 2. Put all the values and you will get ultimately this. Solve this equation, it will give a quadratic equation with respect to E, extent of the reaction, so you will get the answer. Okay, I will not gonna solve it. So this is your job. A hydrocarbon oil viscosity 0.025 Pascal second, Newton second per meter square, and density 900 kg per meter cube is transported using a 0.6 meter diameter 10 kilometer long pipe. So we are transporting, this is 0.6 meter dia and we are transporting oil, but okay, maximum allowable pressure drop across the pipe is del P1 10 megapascal. Due to maintenance schedule on this pipeline, it is required to use 0.4 meter pipe diameter. Okay, so we are using 0.4 meter pipe dia. This is 0.4 meter pipe dia pipe, and this is closed due to maintenance. So now the fluid will come from here, will bypass and will go. Okay, the length is same. To pump the oil at the same volumetric flow rate, that means Q1 is equal to Q2. That is Q1 at 6.6 meter dia is equal to Q at 0.4 meter dia. Estimate the pressure drop for 0.4 meter diameter pipe. Assume both hydrodynamically smooth and range of the operating condition. Fanning friction factor is this. Okay, so fanning friction. So very first, head loss is given by, okay, since fanning friction factor is given, this formula will use. Now in the previous videos I have told you that Darcy's friction factor is equal to 4 into fanning friction factor. This we have fanning friction factor, and this 4F is equal to FD. So I can write this as FD LV square upon D into 2G is equal to HF. Okay, so both are same. Remember this. In 2020 or 21, I think GATE failed to mention whether in a fluid mechanics question whether we have to ask FD or FF. So in the answer key he mentioned both value of both friction factors in 2021, I think. Okay, so now we have this. Okay, so what I did, I just put the value of F here. Okay, now I here put the value of Reynolds number from this and changes this V into 4Q upon pi d square, because Q is equal to area into velocity. And why I have changed? Because it is saying that Q is same. Q is constant in both the pipes, so I have to convert everything in a constant term. So now this whole term become constant. Q is constant, 4 is constant, pi is constant, D is changing only. With respect to D, we have to find rho is constant, V is constant. So now we have to change into terms of Q, because it is saying Q is constant. So we make Q constant, only diameter will remain change. Okay, so in the very next step we will change velocity is equal to 4Q pi d square, and after rearranging, rho is constant, rho F is density of fluid, both it is like this. Rho and F are not different, rho F is this, like this. Okay, so now 4 is constant, this is constant, rho is constant, this is rho F. Okay, 4 is constant, Q is constant, pi is constant, D here D will cancel out, 1D will remain. L is constant, 4 is constant, this whole except D, everything was constant. Okay, so I can write, after rearranging, what I will get? I will get this. I'll get this. Okay, after rearranging, I'll get this. So this C is overall constant. Overall constant except D, everything is in the C. Okay, so now del P is equal to this. Case 1, del P1 is equal to C 0.6. Case 2, del P2 is equal to this. Divide. So we'll get del P2 is 6.86 megapascal. Okay, this is a pretty good question and a little bit tricky as well. A bit tricky. So this is something that again should ask. Okay, so okay, switching over to the next question. This is very simple, but still we will solve it. A free jet of water is produced using 75 mm diameter nozzle attached to 200 mm diameter pipe. Okay, so this is our nozzle and this is our pipe. Showing the figure. If the average velocity of water at plane B here 3.8 meter per second average velocity. Velocity of water at point A. यहाँ पे we have to find out here. Okay. So very first thing, Bernoulli equation. Where at point 1, Bernoulli equation. We have applied Bernoulli equation at this point and at this point. Okay, this is 1 and this is 2. Okay, so C. No head loss, no frictional loss. No pump is there, it is 0. No friction, it is 0. Question is saying no frictional loss. Now, what we have now. So this we have. So PA and PT will be 0 because at the tip when water is flowing out, atmospheric pressure is applying. This is totally in the atmosphere, so both the pressure will be same. So this and this will cancel. Now what we have left with, so this is, now we have to find out VA. For that we have to find out VT. VT is the throat velocity, VA is the velocity at A. So continuity equation. From here we can find VT, everything is given, VT is this. So after putting VT here, we will get VA, and I don't know the answer, but less than this value, maybe 21 or 22 something, maybe 23, I don't know. So just calculate it, that will be the answer. But the concept is, whenever there is the atmospheric pressure is applying, this will be 0. Okay, no pump is there, no frictional loss is there, so equation reduces to this. Okay, next question. A continuous contact extraction column is used to extract a solute from an aqueous stream F using organic solvent S. The distribution coefficient is y is equal to y upon, so distribution coefficient is y is equal to 1x. That's all. Equilibrium relation. X and y are the mass fraction of solute in raffinate and extract will give height of transfer unit based on the extract phase. HTU we have 1. Okay, the rest of the data you can give in the figure, assuming that phase flow rate is constant, not changing. So find the height of the top. So C. This is the question of liquid extraction. But when liquid extraction gives the questions on column, treat it as absorption or stripping. Now this is the condition of same absorption, because in the absorption we mostly have this x2 is equal to 0. We mostly have this x2 is equal to 0, right? So mark it as x2, mark it as y1 0.1, mark it as y2 0.01, mark it as x1 0.09. Now we have to find out height. H is equal to NTU into HTU. HTU we have NTU. For absorption we have solved the what is the formula for NTU. This is the formula for NTU. This is the formula of NTU. Okay. Now the case is of absorption. Okay, so we will find absorption factor. So this is the absorption factor. In the previous lectures I have uploaded all the formulas of absorption and stripping on the same page to avoid the confusion. Okay, so just go and check that, then you will able to understand this question very easily why I have applied absorption formula instead of stripping. If this is x2 is equal to some value of 0.1 and y1 is very small value 10 to 0, then we will apply stripping. Okay, the same as absorption stripping, we will treat liquid extraction column problems same as absorption and stripping. Okay, so here absorption factor is 1. Here absorption factor is 1. Now then there is a special case, NTU is equal to this. Okay, now put all the values, you will get 9. So very straightforward question. So next question, this is also a very easy question, just formula based. I don't think there is a need to explain. Gate 2018, where is the question? Gate 2018 asked the same question, but they changed the value, but the concept is same. Okay, RT made. Okay, so this is the formula, you can see, straightforward, nothing. Okay, so now this is a question that is very beautiful, and if you don't know the cash tree flow, then you will not able to solve this questions. So we'll see this question. A plant is designed to produce 1.2 into 10 to the power 8 kg product per year of an agrochemical. The estimated fixed capital investment is 1.5 to 10 to the power 9. Working capital is 2 into 10 to the power 8, and the startup cost only in the first year of the commissioning of and to be accounted for in the first year 1.5 into 10 to the power 8 rupees. The following cost data are available. Raw material rupees 0.89 per kg product, labor and utility cost rupees 0.27 per kg product, selling price of product rupees 10 per kg, other cost on per year basis including maintenance, insurance and etc. 10% of the fixed cost. Okay, indirect cost, administration cost, R&D, marketing etc. 20% of the sale. Okay, the plant will be fully depreciated over a period of 5 years using the straight line method. Okay, the rate of income 40%. Calculate net profit at the end of the first year payout period. Okay, since this question is from plant design and economics, I'll prefer you Peter S. Max Timberhouse, a very good book to understand the cash tree flow. So we'll see that. So this is cash tree flow. Okay, this is the starting of the company. For a company we need initial investment, some stakeholders are there, some government funding is there, some cooperatives are there. So at the end, at this point our plant is at the position to run. Now this is the period when our plant is making the product before going to the market. Very first time I just erected a plant and I start production, but before going to the market, like I'm making samosas. Okay, but before going to the market, this is the time period. Okay, so now after going to the market I will get profit from the sales, whatever I have sale. Suppose I have sale 20 samosa of 2 rupees, very cheap samosas, so 40 rupees. So this is P. Now we will deduct here all the annual cost which we used for the production. Okay, so P minus A. So net profit will be P minus A. This is the net profit after deduction of all the annual cost. Maintenance maintenance is there, insurance is there, any cost which has rupees per year unit we will deduct. Now in this net profit we will subtract the depreciation. Now we are here, we will subtract the depreciation. In from this cost we will subtract the tax, and this is the money, this is the profit after tax. Now we will again add depreciation, because depreciation amount we just put in our pocket. Okay, so depreciation will be at the end. Finally we will add after the tax. So this is my first year cash flow in my pocket. So we referred as in cash flow, in cash flow, in cash flow, which the amounts are going, we will, like annual monthly we call out cash flow, out cash flow. Okay, so now we will see. So this is the everything we have. So very first, yearly profit, total sale equal to yearly production rate into selling price. So we'll get yearly profit this. So yearly profit is this. Okay. Total capital investment, this. Total capital TCI is equal to FCI. TCI is equal to FCI plus WC. So this is total capital investment. Now raw material. How much raw material we have applied for the production? 0.89 per kg product. This kg product will calculate rupees per year. So this is the our annual cost for the raw material. Utility and labor cost, kg product rupees per year is the utility. Here you see that kg product rupees per year. Okay. Other cost, maintenance, including maintenance schedule, is 10% of the fixed capital investment. Okay, so this is a 10% of the fixed capital. Fixed capital is this. Okay. Now indirect cost of administration, R&D, marketing, 20% of the sale. So 20% of the sale. So 20% of this value is this. Okay, so depreciation with a straight line, this P minus LAG upon N. P is the fixed capital. Or always remember depreciation always always we have to find on the basis of the fixed capital investment, on the basis of fixed capital investment. Okay. So now total annual cost which we will subtract from our sales to get net profit is this. Now net profit, total sales, total annual cost. So this is the net profit. We have to subtract the depreciation. See, we are here right now. Now we are subtracting depreciation. So we are here right now. So this is the value. On this value we will apply income tax. Okay. So we are here. After deducting income tax we will get this. So this then we will add depreciation here, this. So we are here. So this is our final value, cash flow in. Now payback period, depreciable FCI, average profit per year, average depreciation per year, put all the values, you will get 2 years. Okay. So this is the thing. Hope you understand. If you have any kind of confusion, you can comment it. Okay. So the response of a thermocouple, not couple. The response of a thermocouple can be modeled as a first order process to change in the temperature of the environment. In such a thermocouple, 25 degrees Celsius at a 25 degrees immersed in suddenly fluid of 80 degrees Celsius and healthy. Okay, so initially at 25 degrees Celsius the thermometer is, and we are immersing in the atmosphere of 80 degrees Celsius. So this is xs is equal to ys. We have solved these kind of questions, and this is x. It is found that the thermocouple reading reaches 63.2% final steady state. So we have y as well. Y 60.632 of final steady state. Y final steady state. T tend to infinite of this value. Okay. So very first, this is the thing. Now we have this as well, this as well, this as well, this as well. We have to find out the time constant. Okay. So this is x as y as we have 25, x is 80. What is y? So y is the 0.632 of y t tend to infinite. Y t tend to infinite means t tend to infinite means this 80. Okay, so because 1 minus e to 1 minus t by tau, if t tend to infinity, then this whole term will become 0. E to the power minus infinity is 0, so we'll get this. So y is 80. So 0.632 of 80 minus 25, we'll get t is equal to 64 seconds tau. Okay, so this is very simple question, guys. Okay, so a feedback control loop with a proportional controller has an open loop transfer function where the time is in minutes. Obtain crossover frequency ultimate gain. Very simple. First find out the amplitude ratio. This is the amplitude ratio. For this, refer to Donald R. Kaufner. And if you want to read a bit deep, Bode plot, this is the topic of Bode plot. If you want to read a bit deep, go for Asfaq Hussain. But remember, this is book of electrical engineering. Electrical engineering. I don't know the subject. I think, but Asfaq Hussain, electrical engineering. Bode plot is very well explained there. But don't go inside deep. You will understand the graph of the Bode plot. Okay, this kind of graph, like very well explained. Okay, but we'll stick to this question. Okay, so amplitude ratio is this. Now phase lag is this. Okay, straightforward. Now we know that at omega equal to omega crossover, phi is equal to minus 180. So put the value omega is this. Put omega crossover here. We'll get ultimate gain. Ultimate gain is this. So straightforward. This is also a very easy question. So first we will see, given the following block diagram, express the transfer function y upon x as ratio upon x. So y upon x is y upon xs. Okay. So first we will solve this inner loop. That's why I have written y upon x. So since this is negative and this is positive, in the diagram it is difficult to visualize. This is positive. If this sign is negative, then we will make it positive. If this sign is positive, we will make it negative. So suppose this is G1, this is G2, this is G3. So y upon x will be G1 G2 upon 1 plus minus. If it is minus, then plus will come. If it is plus, then minus will come. G1 G2 G3. So this is the formula. So I have applied this formula and I'll get this. Okay, I'll get this. Now this G inner, this become a single block. With the transfer function this. Okay, this becomes single block. Now we have again G1, this whole complete block G2 and G3. So we'll apply the same. Okay, so C upon R will be KC, GS inner, K upon 5S plus 1. Okay, so 1 upon 1 plus, this is minus C, this is minus. So we are adding here. Okay, if this is plus, then we will subtract, but most of the case it is negative feedback. So after solving, you will get this. Now offset is well. So this is our first part, A. Offset is very important. Most of people don't understand what is offset. So we'll see here. So offset is R infinity minus C infinity. What actually it means? It means at t tend to infinite, that means at infinite time when my process is complete, I don't know whatever the time the process has taken to complete, but at t equal to infinite, R, that means RT is equal to limit S tend to 0 S into RS. This is final value theorem. Okay, final value. So I have to find RT tend to infinity. For that, limit s tend to 0, s into what is rs? My rt is what? Rt is 1. How? Unit step change in the response. So it will, rs will become 1 upon s. So 1 upon s, ss. So this become 1. Same thing I did here. Same thing I did here. So R infinity is 1. What is C infinity then? C T tend to infinity, Ct, S tend to 0, S into Cs. Now, see here. This S is this S. This 1 upon S is this Rs. Because when Rs will go there, then we can find complete Cs, na? If Rs will go there, then we are able to find complete Cs, and that is complete Cs. So 1 upon S into whole this term. So this is, now put S equal to 0, everything. So what we will get? We will get this. So this is our offset. Okay. So switching over to the next question. The elementary second order liquid phase reaction A plus B that gives C plus D is conducted in an isothermal plug flow reactor of 1 meter cube capacity. The inlet volumetric flow rate is 10 meter cube per hour and Ca naught is equal to Cb naught is equal to 2 mole or 2 kilomole per meter cube. At these conditions, conversion of A is 50%. Now, if a stir tank reactor of 2 meter cube capacity is installed in series upstream of the plug flow rate, upstream of the plug flow, that means before plug flow we have a mixed flow. At the second case, what conversion can be expected in the new system of the reactor? Okay, so very first we will see. Very first we have a plug flow reactor, case 1, in which A plus B that is C plus D is happening, and the volume of the plug flow is 1 meter cube. So very first rate equation. Since it is an elementary second order liquid phase, so the rate is as per the stoichiometric coefficient. Elementary means rate is same as the stoichiometric coefficient. So we have 1, 1. Okay, so second order reaction, elementary liquid phase. Liquid phase reaction, that means A is equal to 0, no expansion of the volume. Okay. So we will have minus R is equal to 4k 1 minus xa square. Okay. Since Cv naught is 0, because no product is initially, sorry, only A is there. Okay. No, Cv naught is 2. Okay, Cv naught is 2. So we will have this. Now, applying the performance equation of PFR, so we'll have this, putting value of rate, we'll get this. Okay, so K is 5. Now we have a new system. What is in the new system? There is a mixed flow reactor on the upstream, and then there is a plug flow reactor on the downstream of the mixed flow. So very first, now we have K, applying performance equation of plug flow reactor and calculating X is, if this is XA naught, this is XA1, this is XA2. So by applying performance equation of CSTR, we will find out XA1. Okay, because XA naught is 0. XA naught is 0. Okay. Then again we have performance equation of PFR, and integrating XA1 is equal to some value, say X, XA2, then apply, and then we will find out XA2. So it is your job to find out the new conversion in this new system. Okay, it is very easy. Okay, Now, if the stir tank reactor of 2 meter cube capacity installed in the upstream, so first calculate the XA1, then in the PFR, from XA1 to XA2, you have to integrate and you will find XA2. Okay. So it is up to you guys. Okay. So next question. Following liquid phase reaction are carried out in a PFR. A plus C that gives to B plus P. Rate of production of P, product P. K1 Ca Cc. RD K2 Ca. What is the ratio of moles of P formed to moles of D formed at the reactor exit if conversion of C is 50%? No product is present in the feed. Okay. Ca naught equal to Cc naught, 2 kilomole per meter cube, K1 and K2 is 1. Okay. So very first, we know that for PFR, the equation for parallel reactions, in which we are dealing with the selectivity and yield. So this is psi P upon C is selectivity. Okay. So what is the value of selectivity? Selectivity of product with respect to the reactant which is reacting. In most of the cases we deal with the A, but here we are dealing with the C. So RP upon RC will be selectivity. Okay. Sorry, not selectivity, the yield. Because selectivity is with respect to the two products. Like if we have a two product P and D, then we will find selectivity. Here it is yield, product with respect to the reactant. So K1 Ca Cc, K1 Ca Cc. So it is 1. Now, putting this value in the equation, how? This becomes 0, no product present. Okay. Okay, Cp naught, there is no P in the product. Sorry, no P in the reactant. This value we just have calculated. Okay, so ultimately we'll get this now 1. Okay, sorry, this will be Cc. This is Cc naught to Cc. Okay, Cc naught to Cc. So we'll get this because we are dealing with the C, 50% conversion of C. Now again the same thing, RD upon RC. So we'll get this. So this is the answer. Okay, so very simple question. If you know the formula, you can easily do this. Okay. Next, outside surface temperature of a pipe radius of 0.1 meter is 400 Kelvin. Pipe is losing heat at atmosphere, which is at 300 Kelvin. Film heat transfer coefficient is 10 watt per meter square Kelvin. To reduce the rate of heat loss, the pipe is insulated with a 50 mm thickness layer of asbestos. K is equal to 0.5 watt per meter Kelvin. Calculate the percentage reduction of heat loss. So we have to find out the percentage reduction of the heat loss in the second case compared to the first case. So very first, this is the diagram. For first case, there is no insulation. For first case, there is no insulation. This is insulation. So this is no insulation all over the pipe. Okay. So for first case, Q is equal to H delta T, straightforward. We have this fix. In the second case, we have to find out T. What is the temperature? What is the temperature at this point? Here at this point. What is the temperature at this point? So heat Q will be equal to this Q. Right? So Q inside the pipe will be equal to Q outside the pipe. Okay. So because flux is always remain constant. Flux always remain constant. Okay. So we will have this now. From this, temperature is Q in the second case. Okay, Q in the second case, put value of T in any of the n into with 2 pi, because when you 2 pi was here and 2 pi was here, so we just cancel it out. I have not shown this. So by multiplying 2 pi here, this 2 pi, we are getting this. So 419.96 is the Q. Now percentage reduction is equal to 6 to 8.32 minus 4.1 4.419.96. So it is equal to 33.16. Okay, so this is straightforward question. If you have any doubt, any kind of thing, just tell me. Just comment it below. I'll try to answer you guys. Okay. This heat exchanger, one of the most simple question. Okay, so in a 1-1 counter, current flow shell and tube heat exchanger process steam CP is equal to 4.2 kilojoule per kg Kelvin spool from 450 to 350 Kelvin using water. CP is equal to this at 300 Kelvin. The process stream flows on a shell side at a rate of 1 kg per second and water on tube side 5 kg per second. If the heat transfer coefficient is 1000 and 15,000. Okay, so determine required heat transfer area. By what factor will the required area change if the flow is co-current? Tube wall resistance, the tube wall resistance and falling factor. Falling factor. Okay, neglect. So very first thing, what this line means. What this line means. We know that U is equal to 1 upon R 1 upon H naught R naught plus ln R2 by R1 K1 plus ln R2 by R3 by R2 by K2 plus F inside fouling factor, F outside fouling factor 1 upon H out H I. Okay, so this is now tube wall resistance is 0, neglect. So this will be 0, this will be 0, fouling resistance 0, this will be 0, this will be 0. Now the wall resistance is 0, that means the wall are very thick. That means ultimately we will have our U 1 upon U is equal to 1 upon H naught plus 1 upon H naught. Okay, we'll see. So this is the diagram. Okay, then nothing to explain in the diagram. Okay, whatever the conditions given by the question, I just draw the diagram. So for a heat exchanger, heat lost by hot fluid equal to heat gained by cold fluid. Straightforward. This is also. Now we have to find T. So T is this T. Take any one of this MH CPH delta T or MC CPC delta T. UA theta will be there. So as I told you, 1 upon U is equal to 1 upon H plus 1 upon H. Okay. Now this is 600. Put the value. Area is equal to 8.669. It is your job to find for co-current case. Co-current. And you know there is only single difference in co-current, that theta will change. That theta will change because the diagram will be like this. So these temperature, it is 320, 300. So this theta and this theta will change, else remains here. Then you can say by how much amount there is a difference in the area of heat, co-current and counter-current. Okay, so it is straightforward. Now this is the question of evaporators, and evaporator is one of the most interesting topic, I must say. So we will see all the evaporator question in a single video, and I had remembered that I told you guys that I have to make a separate video on catalyst absorption. So we will see that as well. I will not leave anything, and and for particularly evaporator, we'll solve all the questions. But before solving the evaporator, there is a need to understand the concept of evaporator, the equation related to the evaporations, the condensations, and everything. Okay, so we will make a separate video for evaporator because right now GATE is asking evaporator a lot. So that's all, guys. Section B of 2000 is almost complete. We have left with section A of 2000 and 2 marks question of 1999. So we'll see that later. It is just a request, guys. If possible, share and subscribe. And because it took a lot of effort, it takes a lot of effort to write the solution in the PowerPoint, and writing equation is very tough. So Just subscribe if possible and share. Okay, so bye guys, take care.